Welcome to Remote A-Day. Today we are going to go over the Zebra Pens 2 activity, which you can find by going to the Canvas page and clicking on the blue Desmos icon. So we remember our good friend Carol. She comes with a 28-foot fence that we need to set up in a rectangle. Now there are lots of different ways we can set up a rectangular pen with 28 feet of fencing. We're talking about the perimeter in this case. The perimeter is the distance around the shape. Distance around the shape. So in this case it's a rectangle, so we are talking about this distance right here. If we go all the way around, we add all these sides together, we should get a perimeter of 28. So for instance, if we just choose one of these sides to be 4, well, we can think, well, I need them to all add up to 28. So I know that these two will be 4 plus 4. So we've already got 8 feet accounted for. We can take that away from 28, and we know we have 20 left. But we know we have 2 sides that we need to fill in here. And so we need to figure out what those should be. Well, they're going to divide that 20 in half, that 20 that's left, so that leaves us with 10. So each of these sides would be 10 feet, and then you can see if we add 10 plus 10, we get 20, plus 4 is 24, plus 4 more is 28. But we are most interested in area of these rectangles because Carol's got to have room for her amazing dance moves. So to calculate area, we need to do length times width. Or you might think of this as width times height, or however you want to think of a rectangle, but one dimension times the other dimension. So in this case, for area, we would have 4 times 10, we'll put little a there for area, and that will equal 40. So in this case, we have a width of 10 and an area of 40. Now we can make a bunch of different rectangles like this, and we did this in class a few weeks ago in groups. People came up with all the different rectangles we could find, and we tried to maximize the area. And if you go on to the next page here, page 2, you'll see that they have already filled out this table for us, which is really handy. So when the width was 1, they found the area was 13. When the width was 2, they found the area was 24. Now this can be a little bit misleading. I think they've left out a column in the table here, and it'll make sense in a second why they did that. But I want to point out what we're missing here. So we have a width, but we also have a length that is relevant. And when we multiply those two together, we get an area. So we already did like a width of 10. Let me just write these numbers down here. 6, 7, 8, 9, 10. We did a width of 10. We found the length would be 4. And then if we multiply those together, we get the area of 40. So you can see down here, they have width of 10, area of 40. They've just left out that middle column of length, which would be right here. So let's try another rectangle. Maybe we'll choose a different color so we can tell we're doing a different one now. Now instead of choosing the side to be 4, how about I choose the side to be, let's do 2. Okay, we can go through that same process. I know that other side should be 2. And 2 of those make 4. So if we take that 4 away from our total 28, we get 24 left. And we know that the remaining sides need to be half of that, so 24 divided by 2 should be 12. 12 on each side. And we can check that. 12 plus 12 is 24, plus 2 more is 26, plus 2 more is 28. That one does indeed work. So when the width is when the width is 12, the length is 2. We're going to need a few more entries here. So 12 times 2 is 24. And maybe just for fun, let's see, what if it's just 1? Well, we know the other side would be 1. Try to figure out what this remaining side should be. So, once again, we take those 2 away from 28. We get 26 left. And then 26 divided by 2 will be 13. So each of these sides will be 13. So if our width is 13, our length is 1, and we multiply to get the area. 13 times 1 is 13. Now you might now notice a pattern over here in the length. You might see something, we might guess that this one might be a 3 because we see that counting down 4, 3, 2, 1. So maybe let's check. Let's check and see if an 11 by 3 works. So if we did 11, 11, and 3 and 3, well that would be 11 plus 11 is 22, 3 plus 3 is 6, so 22 plus 6 is indeed 28, so that one did work. It looks like this pattern is going to hold, so we could probably just write these in order. And you might notice an interesting pattern here. From the width, we're counting up from 1 to 13, and for the length, we're counting down from 13 to 1. So we don't actually have to write out all of these different rectangles. We can just follow that pattern and then figure out the areas by multiplying straight across. Now something else you might notice, as we go 1 times 13 is 13, 2 times 12 is 24, we might notice that those numbers sure sound familiar. We had a 13 up here and down here, 24 up here and down here. Let's see, 11 times 3 is 33. Up here we have a 3 times 11, which is 33. It looks like we're getting some symmetry. So 4 times 10 is 40, 5 times 9 is 45, 6 times 8 is 48, 7 times 7 is 49. And you don't need to have these all memorized. You are, of course, welcome to use a calculator for any of this. 8 times 6 is 48. 9 times 5 is 45. So we see this pattern where the area is going up, 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 all the way to 49, and then it starts going down, and we have this symmetrical pattern where it's the same numbers on both sides. So this is reflected in this graph that we see over here in this parabola shape. We made that definition before. A parabola is sort of like a hill, or sometimes you'll see it like a U, where it's flipped over. Parabolas are always associated with quadratic. So down below has what type of linear, or what type of relationship is this? We would answer quadratic, because we see a parabola on the graph. And the trickiest part on this problem is to figure out what the equation is. It always seems to be the trickiest part. Well, let's get another page here so we have some room to write. So finding the equation for this one, there are lots of different ways you can do it. This isn't the only way. It isn't the right or wrong way. It's just one way to do it that I think is particularly clear compared to some of the other methods. And that is, we will look at a rectangle, just any rectangle at all, and we will notice that you can divide this rectangle in two. You can divide it exactly in two, like that. And we said the perimeter for this should be 28, right? Perimeter should be 28. Well, if we've divided it in half, and this is exactly half of 28, well, 28 divided by 2 is 14, right? So just this half of the perimeter should be 14 on that side, and it should be 14 on this side as well. So if I just choose any number, let's say 5 over here, I know that 5 plus this dimension should equal 14. I could say 5 plus something equals 14. Another way we can visualize that rather than an equation is we can write it on a number line where we're like, well, there's a 5 here, there's a 14 here, and I need to add some number to get from 5 to 14. We have to figure out what that number is. This is the concept of difference or distance on a number line, and whenever we see that distance on a number line, we're thinking subtraction. 14 minus 5 is going to give us that distance. So we would do 14 minus 5, and we would get 9. 9 is what we need to add to 5 to get 14. So we would say this is going to be 9. Okay, so we'd have dimensions of 5 and 9. And actually, if you come up here to the table, you can see that right here, 9 and 5. Okay, so what if, let's make this eraser a little bit smaller. What if, instead of 5, we chose 4? Well, we do the same process. We do 14 minus 4 equals 10. So we know that other side would need to be 10. And you can again see that up on the table here. We have a 10 and a 4. If we scroll way up, we can see the 4 and the 10 up there. Okay, what if we chose our number to be 7? Same idea, we're going to do 14 minus 7 equals 7. So we know that other side has to be 7. Now here's the part that seems to throw people. That number that we're putting on the side is changing, right? Anything that's changing we can represent as a variable. This 5, this 4, this 7, we're just choosing numbers over there. So we can represent this as a variable that represents a number that is changing. We can call this x. So this dimension of the rectangle can change. And we want to know how this side responds to changes in this side. Well, when this side was 5, this side was 14 minus 5. When this side was 4, this side was 14 minus 4. When this side was 7, this side was 14 minus 7. So we're going to follow the same pattern and say if this side is x, then this side will be 14 minus x. Same pattern. So if we want to know the area, once again we're going to say area equals length times width. Well, we have a length and width of x and 14 minus x. So we should just be able to multiply those. X times 14 minus x. Now notice that I did put parentheses around this 14 minus x because of PEMDAS. We would do multiplication first, but we need this whole side here to be 14 minus x. We don't want to do that multiplication first. We need to get the length or the width, whatever we're calling it, to be exactly that amount before we multiply. So that's why we put parentheses there, so it's calculated before the multiplication happens. And that is actually our equation. Y equals x times 14 minus x. If we type that in here, y equals x times 14 minus x, you'll see it does indeed match all of those dots. And it forms that parabola. So, for the next problems, Carol has decided that she wants to use different amounts of fencing. So she's going to come and visit again, but she's going to bring different amounts of fencing on these problems. So 12 feet for this one, and then if you go a few slides ahead, she'll bring 40 feet, and then also 16 feet. These next ones have the little interactive box that helps you make the box to see if we can make one that has a perimeter of 12, for instance. So there's a pen I made. If I click test it, you can see, oh, the perimeter is 14. It's a little bit too much, so that one didn't work. I need to try again. And maybe I'll just bring this side down 1 and see what that does. We test that. Okay, cool. So that one worked. So here we have the x equals 2. You can see the x is the width. The y is the length. And then when we calculate the area, which it did for you, it's very nice of them to do that, the area is 8. So I see over here where x is 2, I'm going to put in an area of 8. And I need to fill in this entire table. So let's see if we can change the width to 1. I think maybe you might need to make it longer then. We test that. Cool, area goes to 5. We would need to fill all of these in. You see on the next page, those points will be graphed for you. This table will be filled in as you fill in the previous page. And then you just need to write an equation. You will use a process similar to this, or a process you came up with, might also be valid, and figure out how this equation changes. And you can look at how the parabola looks different as well. But we expect it to be kind of a similar pattern, a similar shape, and there may be similarities in this equation as the perimeter changes. So that is an overview of how the ZebraPens 2 activity will work. Please feel free to reach out to me anytime today with email if you have questions or you need any clarification.